from A-Press, there were a load of free copies out there for the first few arrivals. Sorry, there's a hand up? There'll be a load more tomorrow morning at 9, another 50 approximately, right? Well, 49 if I get my copy. Okay, so yeah, the O1 visa, of course, is the big thing. The O1 visa is what means I can actually work in the United States. And so I actually have a piece of paper from the US government which says, and I quote this, I promise you absolutely, literally, I am an alien of extraordinary ability. People occasionally ask me, how come you know so much about Oracle? Well, frankly, if you can do a Vulkan mind meld, it's easy. Okay, so Exadata. Very important point, and this is 100% totally serious, okay? I think this Exadata thing is brilliantly put together. I think it's a wonderful mixture of hardware and software addressing a particular type of problem. It is fantastic technology, right? But perhaps marketing is a different thing from technology, okay? And so I think one ought to read the manual, one ought to examine what's going on very carefully. This is me on holiday, by the way, a couple of months ago. Even when I'm on holiday, I read the manuals. This manual wasn't a very good manual because according to this manual, I was somewhere over there, not where I was standing, but there we go. Fell walking, right? We were going walking through the countryside, sort of up and down bumpy bits. And we got to the top of this rather steep little bit of hill and eventually walked down the other side. And we knew from the map that there was going to be a village at the other side, so we got down to the village and there was a road, and about 400 yards downhill there was a pub, and about 200 yards uphill there was a pub. Well, cost-benefit analysis, right? 400 yards or 200 yards. Not the whole story, downhill versus uphill, right? The real winner was that if you went 200 yards uphill, you saw this sign, right? Absolutely. So off we headed uphill. Trouble is, my eyesight's not very good. I got rather close, and then I could read the sign properly. The point is, you do have to read the small print. And sometimes you've committed yourself too late. Sorry, it's too late, you have committed yourself. I mean, at this point, we were 50 yards from the pub. We weren't going to turn around and walk 550 yards to the other pub. So in we went, and just to add insult to injury, the Wi-Fi router was broken, so we didn't even get free Wi-Fi. Okay, so Exadata. Why choose Exadata? Now, you can find good political reasons, you can find good economic reasons, and you can find technical reasons. But I'm only going to talk about the technical bit of it. How long have I got to talk for? 1 hour or 45 minutes? 1 hour. Okay, fine. Yeah, I have thrown in a few political slides and economic slides on a previous version of this, but I'm just going to go through some of the techie stuff today to highlight the problems of looking at the small print. But I will just throw out this one interesting thought, because I was at the Engineered Systems breakfast seminars this morning, and someone who's fairly senior there came up with a little story about one of their poster companies. I hope that means the same in the US as it does in the UK, about one of their poster companies that started off with 14 servers, 18 databases, and 5 different versions of Oracle, right? And they migrated the whole lot. It was a consolidation story. They migrated the whole lot onto Exadata and ended up with 2 quarter racks. Now, that wasn't, in my mind, a technical thing. What had happened is that the first system was migrated onto Exadata, and it went really quickly. It went so much better. It's not surprising, you know, if just one little system ends up on a very big, powerful box, it does go a bit quick, right? So everyone else wanted to be on Exadata. 5 different versions of Oracle. Which one does Exadata run? So the guy who was responsible for Exadata said, if you want to be on my box, you follow my rules. This is your version, this is your documentation, this is your convention, you do this, 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 and this. And 17 other applications would have been re-engineered, enhanced, improved, stabilized. All the rest of that work would have gone in to make it possible to pass the rules to go onto the Exadata box. And that's a political thing. It's not a technical thing. It's a political point which made everyone clean up the mess and improve their systems. Then, hey, yeah, fine, it goes on Exadata. But can you imagine this guy coming in and saying, hey, I'm the IT director. Today's the 1st of April. Everyone is now going to follow these standards and run version 11.203. It's what they did. But it was sold as, if you can pass the rules to get onto Exadata, your system goes faster. That's good politics. It's not technology. Right? But that sort of political, sort of edging into the economic there, because obviously then threw away, well, disposed of 14 servers, 14 lots of Oracle licenses, and all that air conditioning kit, and cut their electricity bills. Right? But it wasn't about the technicals. Okay, so let's start talking technical. What does Exadata give us? Why is Exadata good? And this is what you should always ask about any bit of the technology. Whether you talk about partitioning, whether you talk about compression, OLTP compression, streams, whatever. What's so good about it? Why might it be helpful? What is irrelevant? Why don't I care? Which bits of it that the marketing people come up with and say, this is great, this is fantastic, are going to leave me saying, yes, fine, sounds very nice, not my game, let's find something useful. And which bits of it are basically going to give you nasty surprises, or nasty surprises if you don't do it right. I always sit here, this is the realist or the pessimist in me, right? Why bother? What's a waste of time? What is positively dangerous? What problems do I have to guess about and work on before I actually risk implementing anything? So what are the unique selling points of Exadata? Well, we've got this sort of smart scan offload type of thing. This is very, very special to Exadata. Apparently, the hardware does it, and the Oracle database software doesn't do it. The disks read themselves and give you the answers. Right? This is almost the way the marketeers come across with this. You've got your Oracle database up here, and the hardware down there sorts out which bit of data you want. Fantastic. Right? So we'll take a little look at that. Storage indexes. We don't even read the bits of disk we don't need, because we know we're not going to need them before we even look at them. I mean, Carrie Millsap is here. What's the fastest way to do something? Just don't do it at all. Let's do a full table scan, but not bother to do most of it, because we know we're not going to need it. So let's look at storage indexes and what the traps are there. Hybrid columnar compression. Right? So this guy earlier on today was saying about how you take your 40 terabytes of database and stick it down into 2 terabytes of disk. He told me he was going to leave. He's going to Gillian's. I assume that's the cafe across the road, but I don't know. Okay, so another thing that we can pick up on, and then finally smart flash cache. I don't really think there's a lot to say about that, but I have just noted this is not the same as database flash cache, so just be aware of the differences in those. Database flash cache, everyone can have, it's not Exadata alone. So let's pick up on what these things are, and let's pick on that by looking at my earliest experience of Exadata. Because I started using what you might call proto-Exadata about 20 years ago. You're supposed to laugh. That's better, right? My first experience of Exadata was about 20 years ago, or what you might call the sort of brontosaurus of Exadata, right? It's evolved since then. I'm in the right bit of America to be allowed to say that, aren't I? Yeah. It's come a long way since then. What do you have? You whack a couple of disks into a box. You stuff in a load of memory, stick in a couple of chips, and you run some software. I couldn't come up with a good picture for software. It's a cloud. Oh, it's a cloud. Fantastic. And it's red. It must be Oracle, right? So we've got this Oracle. So this is it. And then we pile in some very high-speed networks. Right? So you take one of those, and you stick a load of them together, and you pipeline them all together through the networks. And then when you fire a query in at one of these nodes, that node decomposes your query and fires off messages to loads of other nodes saying, go to the disk, get this data, pick out the columns and rows I need, send it back to me. Right? Sound like Exadata? Whoops, Exadata? That's Exadata. That's Exadata 1992, or thereabouts. Right? Your query comes in, it looks something like this, very simple, straightforward query. And actually, the instance that runs that query ends up running this type of code, which is saying, go and select and aggregate from this virtual table, queue, whatever it is. What's been fired down at all the other nodes is something which looks perhaps like this. In capitals and double quoted all over the place, go and fetch PX granules, parallel execution granules. Here's a row ID range from this particular table. Go and get this 128 blocks. Go and get this 64 blocks. Go and get this megabyte. Right? Pick out the columns I need, send them back up to me. This is scanning disks and sending row results. And down at the disks, the other nodes down the bottom there, direct path reads. Rip stuff off the disk, rip the data out of it, pipe it back. That's Exadata, 20 years ago. It's actually an RM1000 running Oracle 7.3.4. But a lot of the technology that goes into Exadata has a very, very long history, has a very long testing path behind it. But this is a sort of starting point, a seed point for Exadata. The good points, what's great about this particular thing? It's local disks. It takes time to move huge volumes of blocks of data across a network so that they can be processed. This thing uses local disks. It's faster to get it off the disk into local memory to the local CPU. The network is a dedicated hardwired network. It's not your generic Ethernet thing, IP running across it in fact, but it's a hardwired RM1000 network, specialized chips. The result sets, what's coming across the network isn't loads and loads of blocks, it's the minimum result set that will get you the answer you want to see. So that's great. What's not so good in this particular early implementation? Every node is a full Oracle instance. There's a lot of software running there. It's not stripped down and optimized to do just the job it needs. Each of those nodes has no detailed information actually about where every other bit of information is. So when a node down the bottom gets a request saying, go and read these 128 blocks, it can sit there and end up sending out a message which says, well, there are 64 of those blocks on that node and 64 on those nodes and none on my local disk drives. Admittedly, those messages go through a special channel, part of the network, which talks more or less CPU to CPU with minimum effort to get to the disks, right? But there's still remote access to disks, okay? We still have this traffic going on, even though it's implemented on Pyramid at a very, very low level. So what does real Exadata give us? Well, we have two types of node. We have the database nodes, I keep forgetting the technology or names Oracle gives these things. We get the thing which runs your actual database up the top there, the compute nodes. We run two layers of instances. We have our database instances. We have an ASM instance. It's pretending to be a sort of file system, file management effect system there, right? Have a few of those up the top. Bottom level, the cell storage, the storage nodes, we have a stripped down minimal Oracle instance. Absolutely bare minimum to run this sort of component, which is, roughly speaking, the parallel execution slave component from the good old RM1000 days. Stick all those together, our network, we can talk from top to bottom. Across the top we can talk, but the cells aren't really going to be talking to each other. They're isolated. And what's the really, really big win on this particular thing? ASM and the cell servers and the disk arrangements and all that sort of stuff about how you handle disks, all those pieces understand and cooperate with each other. So if a database instance up the top says, I need this data, it knows which data to ask for and which cell to put a call to, because ASM and the cells have been negotiating, understand each other, and your database server can say, if I want this megabyte, I send a message to that cell, and that cell says, oh, that's nice, I've got that megabyte, it's right local, I can do what I want. And that coordination between the top and the bottom makes an important difference between the RM1000 and Exadata. Local disk drives, everybody knows who's got what. There is a minimum of cross-chat going on there. In comes our query, we get the same decomposition trick, we get the negotiation, or we will have had the negotiation about where stuff is with the ASM instance. We know the database level knows the database instance has the information. We send the decomposed block range requests to exactly the right place. Typically, we hope to get back just the rows and columns that we really need, minimum traffic. Right? This is the whole smart scan offload bit in Exadata. Biggest win? Local disks, and we only visit the disks for the stuff we really need. We only send back the stuff we really need to send back. Nice technology. Massive history behind it of testing, concepts, and all the rest of it. Right? So I like it. Flash cache, whilst we're on flash cache, it does come in two flavors. Essentially, we've got this sort of level 2 caching mechanism. Except Exadata, in any ordinary Oracle database system, you can whack some flash cache into your machine and say to Oracle, that's a cache. It sort of sits as it's handled by an LRU mechanism very similar to the ordinary buffer cache LRU mechanism. It's sitting there as just one step further away before we just have to dump this stuff completely and go back to disk if we need it. Right. If you actually read the Oracle cores that you've managed to get hold of, there is a reference to an L2 cache, all the pointers which actually behave pretty much like the standard LRU pointers in the buffer cache. This cache down here is manipulated in pretty much the same way in the instance. Here's a funny thing, by the way. I've got God knows how many VMware virtual machines sitting on my laptop. One of them is an Oracle 11.2 running on a 64-bit Linux. I don't have any SSD in any of my equipment. But flash cache is declared to Oracle as a file system. So I just said, okay, I've got a disk drive, there's a file system, it's flash cache. I can address my disks by calling them flash cache faster than I can address them by creating data files. That's weird. Right? I don't know if that's just my machine, but simply by saying this bit of disk is honest, trust me, Oracle, I never ever lie, flash cache, it goes faster. It's bizarre. So we have flash cache. Any database can do that. Right? I have seen some very odd effects, by the way, of flash cache being slower than disk drives on a client side in very strange ways. I've blogged about it on one occasion. But what we have with Exadata is the cell smart flash cache. Right? There is this layer, this massive chunk of SSD sitting there, so that you can either specify deliberately that certain parts of your database should be kept in this cache instead of that just down on disks. You can specify that the log writer should write to this log instead of having to write direct to disk, and so on. And of course, I think we heard in the last 48 hours with the X3, we can now stick something like 40 terabytes of flash cache in here, and it'll be duplexed and totally robust and totally sound, and your entire database will sit on your flash cache instead of sitting on your disks. Right? I have no idea how much electricity that will consume, but you can do it, apparently. I was interested, I mean, here's marketing for you, right? Slide number 7 says you can stick this many terabytes of flash cache in your disk. Think how much database you can put on that. 4 slides later, your flash cache is really safe because it's duplicated. So take this number and divide by 2 if you've been watching closely enough. All right? Yeah. Not terribly keen on every single slide I see for marketing. Is this going to be videoed and sent to Oracle Corporation? Okay, there's too many of them sitting in the front row. What have we got next? Storage indexes. Storage indexes are really very interesting and very nice in some ways. Basically, they're about disk storage. They're not about objects as such. Imagine a disk sliced up into 1 megabyte chunks. That's the way it works. On a chunk, you've either got a megabyte of a table or possibly a megabyte of an index. The storage index thing only works with tables. I could make an argument for applying it to multi-column indexes as well. Basically, it works like this. Oracle can say, if I need to scan this megabyte of disk for some predicate, I can learn what is actually on the disk that might match that predicate. So over a period of time, you might have in memory something which says this first megabyte of disk here, it belongs to a certain table and there's columns X, Y, and Z. And in this 1 megabyte, the low and high values of column X are this, the low and high of column Y are that, and so on. And the very next megabyte on your disk might be a bit different, same table, but the storage index might say, well, I've only got information about columns A and Z. And the next megabyte could have a collection of bits of information about other columns. So megabyte by megabyte, Oracle has some idea of what rows from particular tables are on that megabyte of disk. Right? And if it's got that sort of information, it can avoid, in memory, just a very brief summary, it can avoid reading disks. Now, the rules about this at present, you can record storage indexes in memory of up to 8 columns for each table, right? So a little thought of how they work. Let's say I've put in a query, Oracle's decided that it's going to start doing table scanning, and it's sending out smart scan calls, 1 megabyte at a time. And it's sending out calls which are effectively saying, get data from this disk where column X equals 99. Each megabyte call hits the system. The cell code says, okay, I've got a storage index for column X on that particular megabyte that you're asking for. You want 99, and my storage index for this megabyte says, I've got values between 10 and 100. Therefore, I have to read that disk. The next call comes from the front end. Same predicate, of course. The cell server says, I've got a storage index for column A, column Z, nothing about column X. I've got to read the disk. The next call comes in for another megabyte, and, oh, sorry, when we read the disk, of course, we're looking at what's there. We can actually create for that megabyte a storage index entry for column X, for that megabyte. So having done that scan, we've added to the storage index information. Next megabyte call comes through, and Oracle says, column X, it's between 200 and 350 on this megabyte. So I don't need to look at the megabyte. And it can return very promptly an answer saying, don't scan the disk. Okay, 1 megabyte at a time. And you'll notice different megabytes can be referencing different columns in their storage indexes. It's not something which says, across the entire table, I've created a storage index for the whole of column X. Every single megabyte can have a different pattern of which columns happen currently to have this summary information in them. Now, this leads to some interesting side effects. Okay, oh, I just threw up, let me just go backwards there a moment. I just threw up the statistic you see. If you're using storage indexes effectively, you'll start seeing statistics about how much physical I/O you did not do, how much you carry optimized by using storage indexes. Right? So what sort of things happen? Well, here's a very simple test. Okay, created a table with a few columns in it, started running queries. Select where column 1 is constant. Right? And this is a slow query. There's no storage indexes. Run the same query again, and it's quick, because by this point, the storage index for the entire table on that column has actually been built. It's the first query I've run on the table. Okay? Do it for column 2. The first one is slow. Repeat it, it's quick. And we can carry on all the way through 8 indexes, 8 columns, one after the other. The first query is slow, the second query is quick, because there's nothing built in storage index so far. Each first of the pair builds an index, the second of each pair uses that index to do less work. Okay, column 9. Run that query and it's slow. What happens when I repeat the query? Is it slow or quick? Someone says slow. Because I can, sorry? Hands up, okay. Who thinks it's going to be slow? Who thinks it's going to be quick? Who thinks it's going to be maybe somewhere in the middle? Who wants to compromise? Right? It's the compromise. Well, no, I can't guarantee that, but it might be the compromise. Right? There's potentially an LRU algorithm. There's potentially an effectiveness algorithm. When I actually did this, that second query run was faster than the first one, which means as the first one ran, it kicked out some of the other storage information that was there on columns 1, 2, 3 through to 8. And I could check the statistics. I ran the query against column 1, and it was slower because some of its storage index had disappeared. I reran the query against column 2, and the result came out slower because some of its storage index had disappeared because the query 9 had kicked out some of 1 and 2. And there are various algorithms, I believe, which are, as I say, LRU. If you haven't used the storage index for ages, perhaps it drifts out of memory. If Oracle looks at it and says, do you know this chunk of storage index here says the low value is 1 and the high value is 15 billion, I'm never going to avoid going to the disk because these values are so wide. I can throw away this one chunk. Whereas the next megabyte, the same column says the low value is 1 and the high value is 3. That's going to be a useful bit of storage index to keep. So there's algorithms relating to the potential effectiveness, probably. Haven't tested all of this yet. So there's a potential for interesting variation in performance as you go through storage indexes. They flush and cycle. You can't control them. Here's another thought. 3 queries, running them one after the other. Select where column A is constant and column B is constant. First run, it will be slow. Run this query. Just select for column A is constant. That'll be quick because we've got the whole storage index. We scanned the table for the first query. We've built 2 storage indexes simultaneously across the whole of columns 1 and 2. Second query will be as quick as it can be. The third query will be as quick as it can be. Reboot your system and try again. Let's do our query for column A equals constant. It's slow. What about this? Select where column B is constant. It's slow because there isn't a column B storage index yet. And then this combined one will be quick. Okay, reboot. Column A equals constant. Column A is constant and column B is constant. Is that going to be quick, slow, very quick, very slow? It's going to be pretty quick because it's got all the stuff which is, I will only visit this for column A, and then it's going to check column B, but only for the stuff where it really needs to go and check for column A anyway. It knows which bits of the disk have got the right column A. Those are the only bits it will check for column B. So it pre-eliminates loads of stuff. So what happens when you run this? Select where column B equals constant. Is it fast or slow? Lots of voices say slow, and they're right. Well, sort of slow-ish. It's not great. It's faster than slow, right? But not as fast, right? Because when we did the second query, we will have actually got a little bit of storage index built for column B, and that's probably going to have helped, but there's potentially all that stuff which we didn't read because column A helped us, we've now got to read that. So you've got 3 queries here. The performance of those 3 queries depends completely, well, not completely, very strongly on the order in which you run them. Isn't that great? Of course, in a sense, that's true on any Oracle system, right? Because when you run a query, you cache data, right? And if you're lucky and run your queries in the right order, you keep taking advantage of the cache you had before. Really useful bits get heated up and get into the hot bit of the cache, and the pretty useless bits sort of fall off, and your cache becomes more and more efficient. But you can get some really strange effects here, extreme effects. And I mentioned this business earlier on about the effectiveness of a storage index. Just as a very simple example, I've got one of my classic clustered and scattered data. Use mod to cycle through numbers so you get very scattered data. Use trunc to produce clusters of the same value. You know, divide by 1,000 and truncate, right? You get 1,000 of the same value one after the other, and then create storage indexes. Your scattered data, 0 to 999, and recycle. Your clustered data has all the 1s, all the 2s, all the 3s, and so on. Well, if you get a storage index on the scattered data, every single value of that data appears in every single megabyte. So a storage index gives you no benefit whatsoever. If you create a storage, or rather if Oracle automatically creates a storage index on the clustered data, a given value will appear in precisely one single megabyte chunk. A storage index on that second set of data will be fantastic. Because Oracle will say, yeah, there were sort of 3,000 chunks of data I was supposed to read, but yeah, I actually only read one of them because I knew I didn't need to read the other 2,999. Right? So ordering of data can make a massive difference to the effectiveness of storage indexes. Just some of these things that you can think about to change what's going on. The storage indexes. Wonderful opportunity for destabilizing your system, but perhaps engineered correctly and carefully, being aware of the traps, you can get some interesting benefit out of them. Okay, I've forgotten to put my clock up, so I have no idea what the time is. Oh, that's brilliant, yes. And it's not on my screen, how strange. Okay, so I've got half an hour left, is that right? Oh, half time, terrific. Yeah, okay. So hybrid columnar compression. I love it. It's fantastically brilliant, right? What do you get with compression? Well, basically, more rows per block. This is a good thing because you don't have to read so many blocks from disk to get all those rows out, right? This is a bad thing because it takes more CPU to pull them out of the block and decompress them, right? It's a bad thing because it takes more CPU to squeeze them into the block in the first case. And it's a bad thing because if you start changing those rows, you've got more of them in a single place, and if lots of people want to change them, you get more people fighting over the same tiny space. Now, this isn't just hybrid columnar compression, it's compression full stop, right? Compressed indexes, compressed tables, compressed OLTP. The better you pack your data, the faster you can, in principle, query it, because you physically have to pick up less of it, but the more expensive it is to play with, and the more contention. The better the focus of contention. Just classic compression. Where's the trade-off? Oracle gives us as a license option, compress for OLTP. That's basically actually a deduplication trick. It's got all sorts of interesting and nasty side effects if you're unlucky, right? I'm not going to talk about that, which is why it's in gray. I'm just going to talk about hybrid columnar compression. It comes in sort of 4 combinations. We've got query or archive, low or high, okay? Hybrid columnar compression, because this is the thing which is really, really different and lets you pack masses of data into a tiny space, right? So how does it work? Well, essentially, Oracle says, okay, I've got a batch of rows here, maybe a couple of hundred, maybe a few thousand, maximum 32,759, right? Don't ask why, I've got no idea. I will take a load of rows. And from each of those rows, I will take column number 1 and produce a batch of data in order, which is column number 1, and then do some whizzy compression on it. And it might be, I don't know, Lempel Zev, it might be bzip, gzip, gzip plus, or whatever. It applies a compression algorithm to produce a mass of data. And for each column in turn, it does the same thing. Keeping the columns in order, right? We maintain the row order, we compress each column separately. And then we just string these mega columns together. So we have a compression unit, a thing. Our final object is a compression unit. There's a little header section which describes the rest of the data. A bit further down we see this is the big blob, which is column 1. There's the next one, which is column 2, column 3, column 4. In effect, it's like a single row of 4 columns. Oh, the gap I've left in the middle there, there's pointers from the header into where the 4 columns start. The gap I've left in the middle is a bitmap. It's a bitmap which is just basically 1 bit for each row that exists in that compression unit. And we'll see what that's used for in a little while. So that's a compression unit, right? A few numbers. In archive compression, I think this can be as big as 256K. A single unit can be huge. If you're doing query, query low, query high, I think the limit is 32K. I say I think because I haven't been able to force larger sizes. I cannot prove that's right, but I haven't been able to do any better. And my figure, 32,759, I've run up examples where really, absolutely, definitely Oracle, if it could do more, would have done more than 32,759. 32,759, bizarre though it sounds, seems to be the absolute limit for the number of rows that can go into a single compression unit. So that's a compression unit, and they can be big. And Oracle treats a compression unit in one sense as if it is a single row in a table. So how does Oracle store this in the database? Well, in a database, we have blocks. Right? So here we are, there's 4 blocks, 4 block boundaries there. And a block has a block header and a row directory. Right? So let's stick our compression unit, and there's our 4 blocks there with 4 row headers and 4 block directories and 4 row directories. Let's stick our 1 row into this set of 4 blocks. So we'll start just plastering this compression unit into the first block. To do that, we need to put an entry in the row directory which says I've got 1 row and it starts here. Right? So that's where we start our compression unit. And our compression unit rolls itself out into the block, and oh dear, bad luck. Our compression unit's about 30K long. It doesn't fit entirely into the block. We get to the end of the block before we get to the end of the compression unit. So Oracle says, hey, that's okay. I do chained rows. So our row header, the orange bit, points forward to the next block and says, insert a row piece in the next block. And the next piece of our compression unit goes there and fills the block. And we've still got a compression unit left, so we point forward and forward. And our compression unit ends up being stored as, in this case, 4 row pieces, and each row piece has a pointer to the next row piece. And if our compression unit was the maximum size, that 256K, that would be 32 consecutive Oracle blocks chained one after the other, a single row of 32 row pieces that create the compression unit. And there is this slightly funny little thing. A compression unit on one hand is a single row in terms of finding where it starts and it's chaining onwards to reconstruct, and at the same time it's potentially 32,759 rows. So if you have a row ID, someone says, I've written a query, it's pulled a row ID from this database, how do I get the row that is that row ID? Well, Oracle sort of splits it in two different ways. You can have a row ID, a compression unit, which says it's file number 5, block number 93, row number 32,107. Well, the file number and the block number with a 0 on the end of it gives you the row ID for the row where the block actually starts. Oracle can derive the row, the starting point of the compression unit. And having done that, it can say, okay, so I've got a compression unit, which if I decompress it, I can now turn into 32,759 rows, and I know where each column in that row starts in this great long strip. And if you want 32,103, I know how I can decompress and walk along this thing and find the 32,107th row in the compression unit. So we actually have two different ways of treating that row ID. The starting part of it tells us where the compression unit begins, and then the final row portion of it actually tells us whereabouts through the compression unit we want to be. Okay, so that's putting a compression unit into the database. I think I'll just make one more point before I show you the next slide. How do we select a row from here? Let's say we said select column 1 and column 4, where column 3 equals 99. Right? As Oracle is perhaps scanning through this table, it will pick up a compression unit, and it will say, our where clause said column 3 equals 99. So I need to pick up, and I'm going to have to pick up the first block of that compression unit. I will point forward to the next block because that's where column 3 starts. I can look at the start of column 3. I can expand column 3. I can go through that column 3 and say, yeah, rows 17, 99, and 114 match the where clause. So I've got 3 rows which I've identified from column 3. Now let's go back to the compression unit. What do I want? I want column 1 and column 4. So let's pick out the column 1 section, decompress it, pick out the 3 items I need, find out where column 4 is. Oh, I've got to chain another couple of blocks along here, pick out the column 4, decompress it, find the 3 rows I need. Now I can send 3 rows back up to the database. There's quite a lot of work goes into picking out a couple of rows from a compression unit. A compression unit which can be 32 blocks long and hold 32,759 rows. Right? Okay, so compression units. A couple of points about compression units. Compression takes place at the database server. Right? So all the CPU for compressing happens up at the database server, the bit where you pay the license fees. Right? Decompression tends to take place at the storage servers. If you're doing a table scan, the cell server code scans the tables, decompresses, extracts, and all the rest of it, and pipes rows back up to the database server. Except, oh, and that's okay to burn up that CPU because you don't pay licenses for those. At least that's the way Oracle thinks about it. Right? You pay licenses for disks. Am I right? You pay licenses per disk? No. Sorry, you don't answer license questions. Okay, they don't like being licentious. Okay, the way I've heard it, you pay per disk, right? It's purely a coincidence that the number of disks matches the number of CPUs, right? You pay licenses per disk. Okay, fine. You don't pay. The CPU you burn up is down at the cells. It's not nominally where you're paying license fees. Okay, but you don't always decompress down there because sometimes it fails, and the blocks get sent up to the CPUs, which you're paying expensive licenses for, and the CPUs up there have to do the decompression, and I'll show you that in a little while. Okay, so what other things do we do? Well, if we've got HCC in place, we tend to avoid deleting rows, but we can. This is where the bitmap comes in. right? If you want to delete the 99th row in this compression unit, you just mark the bitmap as 1. It's deleted. That gets rid of it. You have to go and delete the index entries, of course. If you want to do an update, you don't. You delete it. You delete the row, but first you decompress the compression unit, read out the entire row, then you mark the row as deleted, then you insert the row somewhere else, not using HCC compression, but using ordinary OLTP compression. You delete all the index entries, and you insert index entries which point to the new location. So basically, once you're into HCC, you think very, very carefully about how much deletion and how much update you are going to allow, because it is expensive. It's not a nice or sensible thing to do, right? I mean, Oracle's not trying to fool you when they tell you this stuff about HCC and being brilliant, but you really do need to think for yourself, how much data change might I have? How does that affect my decision onto whether I do HCC and how much I do? I've actually talked through accessing a row by row ID through an HCC compressed unit, so I won't actually say very much about this particular slide here, except for the very last point. If I've accessed a compression unit, pulled it into the cache so I can decompress it, because that's one of the occasions when we decompress at the database rather than down at the cell. If I want a row, I pull the cell of the compression unit to the cell and do decompression there. Where does it decompress, and how long does it stay decompressed for? And the answer is, if you want one row from the table down there, you may end up pulling the whole 32 blocks back into memory, figure out through decompression in your PGA what the row looks like that you actually want, and the moment you got that row and go off and do something else, you throw away the entire decompressed compression unit. That's rather important because of this demonstration. I set up the table there called T1AH, AH for archive high. I set up this table with only 32 million rows in it, so it's just a tiny little thing. That column there, N128K, it's one of my mod type columns. I've got 128,000 distinct values in that particular column. I'm going for value between 1,000 and 199. But I've generated the data cyclically. So 1,000 exists here, and then there, and then there, and then there. It's scattered very widely through the table. Okay? I've blogged about this one. It's very entertaining. Having created that data, archive high, right? I'm going to do something insanely stupid, right? I'm going to select some of the data. I've got that query, which says select, it's 256,000 rows. Now, I started off with my base table, right? And created an index, which was suitable on this particular column. And I ran the query. It's amazingly fast stuff, this Exadata stuff. This query completed in 0.7 CPU seconds of basic, standard, no compression data running through Exadata, index access path. Query high. The same query, when the data was compressed to query high, took 77 CPU seconds. Yeah. This was the older system. Yeah. Okay, we've got a suggestion here that compression may go faster and use less CPU on different systems. I will come back to that in just a moment. Okay? Okay, so query high. Anyone want to guess what it took when I ran to access archive high? 200. Any advance on 200? No, it's not still running. But if I'd started the query running when I started my talk, it would still be running, right? 3,000 CPU seconds. The V2, is that the older kit? This was V2. On an X2, it took 2,700 seconds, right? This is your expensive CPU burning away to run a query that takes 0.7 of a second if I don't use Exadata. Or rather, do use Exadata, but don't use the Exadata features. Sorry? Yep, revenue, absolutely, love it. What have I done? It's this business of when do you decompress and how long do you hold it for, right? There's 5 consecutive compression units. When I pick up 1,000, there's one in compression unit 1, there's the next one is in compression unit 2, but when I pick up that one, I throw away the decompressed compression unit 1. I decompress the second unit. I go to get the third row, which is in compression unit 3. I lose the content of compression unit 2. So I decompress 3, and I go round and round. And I get to the end of the thousands, and I want the 1001. Well, the first occurrence of 1001 is back in compression unit number 1. I decompressed a very large compression unit for every single row I wanted, despite the fact that I could have got away with decompressing about 200 compression units if I'd decompressed one unit, got all the data I needed between 1 and 1000 from that, then gone to the next unit, decompressed that, and used it as much as I could, and so on. But the optimizer doesn't know how to do that. The runtime engine doesn't know how to do that. It simply says, I did an index access, an index gave me a list of row IDs, I went to each row ID in turn. And I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and every single time it was decompress, throw away, decompress, throw away, decompress, and go round and round and round 1,000 times. Bloody quick for what it did. Bloody stupid for doing it. Right? I fixed it. Okay. I realized, well, actually, I knew what was going to, well, I didn't quite know how bad it was going to be, but I knew what I was doing when I did this. Almost. Right? So I fixed it. Here's a query which says, well, don't get the data, just get the row IDs. Right? And when you've got the row IDs, sort them into order. And when you've got the row IDs in the right order, nested loop. For each row ID that's now in the right order, go and get to the table by row ID. So I sorted the row IDs, so all the row IDs for compression unit 1 were together, then all the row IDs for compression unit 2, and so on. I visited each row ID, each compression unit, and decompressed it just once. So how long do you think that took? Any guesses? 16, well, yeah. That's a damn good guess. 16 CPU seconds, right? 16 CPU seconds at the database server. Interestingly, if I just said to Oracle, do a table scan, it went into a smart scan and took 22 seconds. What's the difference in CPU between 16 seconds and that 22 seconds? Sorry? The 22 has got all the cell servers. Effectively, the table scan is running in parallel because your database server can say, cell number 1, get me a megabyte 2, get me a megabyte 3, get me a megabyte 1, you've got it, fine, get another one, and it basically runs in parallel. I actually had 3 cell servers on this particular one, right? So that 22 seconds at the database server is 66 CPU seconds down at the far end. Right? That's an interesting trade-off to consider. The thing you really need to protect probably is your database CPU. So what's your better bet? Doing it the 16-second way up here where it's expensive to license, or down there where it's vaguely sort of free of charge, but 66 seconds or 14 times as much if you've got the bigger server. Right? It's a very important thought. Dan? Yeah. Right. Yeah, if you do different decompression, if you do different compression levels, do you, and you keep the data in the same order, do you change your clustering factor? The answer is basically yes, mostly because if you do compression, say query high, you turn into something which is 4,000 blocks. If you do archive high, it's 1,000 blocks, and therefore, almost accidentally, the clustering factor is a quarter of the size. Oh yeah, yes, yeah, yeah. The clustering factor calculation is the same, right? Okay, so here we go. I've got my wonderful clever trick. I've solved Oracle's problems for them. This is my execution plan. I do a sort order by materialized there through that view at line 3. Nested loops, I get 16 seconds, right? Oracle produced a patch. It's not yet available, or at least Maria said the last time she spoke, it's not yet available, but this is the plan you will get in a patched version of Oracle doing the same thing. Oracle has caught up with me. They will now run this query in 16 seconds because they've introduced a sort order by which says if you're on Exadata and you're querying compressed data, you need to make sure that you sort the data by row ID, the row IDs by row ID, before you visit the data. Otherwise, you'll be decompressing compression units too frequently. So you will see plans which say do an index range scan, do a sort. That's getting the row IDs in order. Now go and access the table. Just an interesting throwaway point, by the way. This problem happens everywhere in Oracle. It's the nature of range scans on B-tree indexes. It's just that you don't see it normally. I mean, in the past, I've done exactly the same optimization trick on large data sets, because in the past I have seen this range scan going, read a disk, read the disk, read the disk, and we do random reads as we range through a table, and we come back and we reread a block which we've lost in the last few seconds because so much activity has been going on. And optimizing means read the block once from disk, right? So I've used this trick for years on very rare occasions in just standard Oracle. Exadata HCC makes it very, very easy to see the problem. Now I have a, where did the clock go? Who's switched off the clock? It's okay, it's midnight, I don't care. Okay, failure, right? Smart scans can fail. I ran this query, it's T1QH, it's the query high version of the data. Right? It's very, very well compressed data. It's brilliant compression, but it's only query high. I've arranged my data to compress fantastically well, sorted it into the right order. That helps compression. Okay? So I've just run this query here. The statistics I get from this query are as follows. The interesting ones, compression units sent uncompressed. Okay? Compression units decompressed, 17,900. How many query high compression units are there for decompression? 12,300. This table is 12,300 compression units, but I really have decompressed 17,900 of them. Why? Because I failed on 5,600 of them at the cell and I sent them out to the front end. Now, the way cell communication works, this chat back and forth between the database server and the cell, is that the database says to the server, smart scan, give me a megabyte's worth. Here's your megabyte block addresses. And the cell says, okay, I'll hit that megabyte, work out what's in it, and bang it back to you. And if what's in it expands to more than 1 megabyte, the cell says, 1 megabyte is the maximum message size. And I've just expanded to more than a megabyte. So I can't give you the rows and columns. I've got to give you the cell, give you the compression unit. You have to decompress it. You get sent uncompressed, and you get more decompression than you actually have original compression units. And here's something truly brilliant. When the cell decompresses, every single cell server is working in parallel. When it pumps back to the front end, if that wasn't a parallel query, the 5,000 cells, which was, sorry, I keep saying cells, the 5,000 compression units that were spread across 14 cells are now decompressed by one CPU. It takes 14 times as long to do the decompression at the front end as the time it would have taken at the cell if you'd been allowed to survive from the cell. So you can actually compress too much. Right? If you're really, really good at arranging your data to compress it fantastically well, you can find that your front end does all the decompression. Now, in many cases, this probably won't catch you by accident. But I have seen an awful lot of data warehousing ETL types of systems which say, hey, I've got rows which are 500 columns wide, and that's another whole story. I've got rows which are 500 columns wide, and I run queries which say, get me 300 columns from this table, join to 260 columns from that table, and send them off to SAS. Well, if you fetch lots of columns and you manage to get good compression, you're almost guaranteed to decompress at the cell, blow up, fail, send it forward, decompress at the front end. There are applications I know of which will hit this 100% of the time. Right? And they're paying massive amounts for the CPU, which they're burning up at the front end. Okay, so that's just a sort of textual note about what's going on there. So we can fail. And we do come back all the time to a basic optimizer problem. The optimizer hasn't got a clue about Exadata. Well, not quite. Okay, what do we do with optimization? A fundamental point of optimization is this. I've got 4 rows in a table, the blue lines, 4 rows in a table. I've got an index which is perfect for access precisely to those 4 rows and nothing else. Should I hit that table by doing a table scan to answer that query? Because I can just whack out 3 big chunks there. I've got 1 read, which is the segment header, but that's maybe in memory. Should I go for 3 big reads to get that data out? Or should I go for using the index? And the optimizer has no idea about the fact that those reads might be reading compression units. That those reads might simply disappear because of storage units. The optimizer has no idea what it's going to cost to do that table scan. Oh, and of course, what it's going to cost may vary hour by hour, because storage indexes drift in and out of memory. Right? Or should we go by index? And if I go by index, well, we do these single block reads, and indexes often end up cached in local memory, so that's kind of okay, and we pick up those 4 rows by single block random reads. And the optimizer has no idea that those single block random reads might each be a 32 block chunk which has to be pulled back across the system and decompressed massively, and then find that the process has to be repeated time and time again because it's doing a range scan and doing that cyclic thing. The optimizer has no idea what can go wrong with Exadata. And yet the arithmetic has to work out whether to do a table scan or use an index. Not a hope. Well, not always. You have to help. Now, I pointed out that Maria had given us this thing which says we can deal with the compression unit and random access by row ID. Honestly, if we're doing archive high, we're probably not expecting to do high precision queries, right? I've got this 4 terabyte database and I want to do high precision queries. Really? 1 row at a time? Maybe not. So if you're thinking sensibly and compromising a little bit, trying to think through what you're likely to do, perhaps you can help the optimizer out a little bit. Maria's told us there's this order by row ID thing coming in some future patch. What about the other business of trading off table scan costs against index costs? Well, just think about this. If you have your traditional hardware and you have rows, if you have sane rows, a couple of 100-byte rows, you might get 40 rows per block. If you want to get 1 row out of, say, a 16-block multi-block read, when do you trade off between 1 read is 16 blocks, which is 640 rows, or 1 read is table scan chunk, right? There's your sort of balance point. 1 row out of a small number of hundreds is about the break point between choosing an index and a table scan, right? You can argue about the numbers, but that's the sort of ballpark. Do you remember the things people say? If you get less than 5%, you do an index and all the rest of it? There is a sort of rationale in that if you've got the right numbers to back it up and explain what you're trying to achieve. We're talking 1 in a small number of hundreds. There's your break point. Where does your break point come in Exadata? When you can say stuff 32,000 rows into 32 blocks and you do a megabyte read against that, so you get 4 of those compression units in a single read, right? Your break point turns into something like, if I want 1 row in 500,000, perhaps I should use an index. We don't really know. We still have to find out and practice on it. But the optimizer hasn't really got a clue. There is one other little change that Maria Colgan mentioned. It's a patch which is already available, which basically says when you run DBMS stats, one of your options is to say DBMS stats, set the system stats for Exadata. The only amazing thing that this does is to say MBRC, the actual multi-block read count, MBRC equals 128. When we do table scans, we get lots of blocks in each read. And that tends to say to Exadata, sort of it slightly improves the balanced choice between indexed access and table scan. But really, the optimizer needs a lot of help. Right? We probably don't need many indexes if we start playing games with what Exadata can do, but actually picking the right ones and making sure we use them at the right times, it's a bit tricky. So, endpoint. Does anyone know what the time is? Is it 4 o'clock? Is Christian champing at the bit? 4 o'clock. Okay, endpoint, right? There's not a lot in Exadata which says we're good for OLTP, but politically, you might want to stick loads consolidation. It's a good political move, right? It's new, fast, efficient, fantastic hardware, right? It's not magic for OLTP. It's magic for data warehouses, but, you know, magic is a bit dangerous. Magic is unstable, right? Storage indexes can cause interesting instability. You need to think very carefully, possibly about switching them off. Possibly about engineering a few cases very, very carefully so that what happens automatically is actually what you want to happen. And compression levels, think extremely carefully, because you can be too good at compressing and pay penalties elsewhere. And as for indexing, damn, it's hard to figure it out. All you can say is you probably need to have a lot less, and you probably need to design them very, very, very much more carefully than most people currently do. Okay, it's time for Christian to have his go. Thank you very much.